Two names are homonyms? Because if you do, you definitely don't have a New Jersey accent. This is pronounced Don, and this is pronounced Dawn. It's totally different, right? Like I remember there's this episode of Mad Men where like Don's secretary is named Dawn, and everybody has like a Long Island accent, and they're like, how do you tell you two apart? And everybody's like, Don. Thanks for saying it. It's like, it comes out certain words like water and coffee and claws.
I was going to say, it wasn't even that bad. You could say water.
Right, you can say water with W-A-W-T-E-R, water, not water. You know, people from the Midwest are like water, it's pronounced water.
Yeah, you're also not saying water.
Secret 30 and then we'd say it.
Alright, anyway, I guess it is 2:40 now, so let's begin. Hi everybody, welcome back after the midterms. Everybody still feeling okay after the midterm? Seems like it was alright, right? Everybody felt like it covered the material that we felt like we were expected to know. And I want to say I'll have them graded within a week of the midterm. It's probably going to be more like a week and a half. But definitely within 2 weeks you'll have the midterms back, so that you can think about what you know and what you don't know. So what I would like to do is like make a really kind of quick segue in which I say a few more words about replication. Because there's a replication regime that we didn't cover that you may have noticed if you looked carefully at the review sheet called state machine replication. And I think like this is an interesting replication protocol to study as we transition into talking about agreement and consensus and totally ordered messaging and things like this, because it's going to turn out that state machine replication, like all strongly consistent replication schemes, establishes a total order, and it does it in a really interesting way that we haven't looked at before. And then once I've gotten that out of the way, we'll sort of be done with replication. We mostly won't be talking about it anymore. We'll be moving into probably 3 weeks of trying to tackle what it means for a collection of computers to agree about a thing in a fault-tolerant way. So, state machine replication. There's one respect in which state machine replication looks completely different from all the other replication schemes we've looked at. And it has to do with the type of computations that are being replicated. State machine replication can make multiple copies of an arbitrary computation, you know, with a footnote, obviously, where there's going to be some restrictions on what I mean by arbitrary. Not just reads and writes to shared variables like we've been studying, right? So chain replication, quorum replication, primary backup replication. Our model of the world was there's this universe of variables, x and y and so on, and clients connect to replicas and they write variables and they read variables. Okay. State machine replication is going to give us a way to generalize this and say, it doesn't just have to be a key value store, if you like, that you're replicating. It can be any computation that you might ever run on one computer, subject to some constraints, I'll tell you in one sec. If you can run it on one computer, you can plug it into state machine replication, you can run it on many computers and exponentiate your probability of failure in the way that I said. That's really powerful, right? Any computation that was ever designed to run on one computer, I can run on many, provided that it is what do you think I'm going to say? Yeah, I mean, then it is a state machine, right? So that it is deterministic. Okay. What is a state machine? What do I mean when I say provided that it is a state machine? Yeah.
Well, a state machine is a set of states.
Great. Let's write it out. Hang on. So it's a set of states. Okay.
That have connections from one another based off of operation.
Yeah, but how do we write the transition function? The function is in a relation R from states to states, right? That is it's not a relation, it's a function, right? Now, how do we do this? Sorry, I haven't done the formalism in a while. So it's a set of states, and it is a function from states and inputs to new states, such that that function is deterministic. If I'm in a particular state and I'm given an input, I take a transition to another state. And together these make a state machine. So what might a state machine look like? Well, a state machine for something like, oh, I don't know, a soda machine might look like, well, there's an initial state where the thing's sitting there with no money in it. And there's a transition that says, add a quarter, that takes you to a new state. We'll just call it 1, I don't know. And then there's another transition called add a quarter that takes you to a ready to dispense state. And then if you push a button, it dispenses and takes you back to the initial state. And then there's like, I don't know, there's a cancel transition that you could take too to get your money back, right? So you see how like this is the same as this, right? The circles are the states, the arrows are the function. It is the case that for a given label and a given arrow, there's only one thing that it can point to. So this thing is deterministic, right? So what does it mean that this thing is deterministic? It means that if I have 2 copies of this state machine, I'm not going to draw the whole thing. Let's say I have another copy of it. What would I have to do to make sure that the 2 copies of the state machine were always in the same state? I would make sure they got all the same inputs. What else? In the same order, right? Because if I do them in a different order, I don't necessarily get what I expect. And maybe in this one I did, right? Yeah. No, because there's going to be invalid transitions, because B is not a valid transition out of something. But in general, you're not going to get the property that the machines are going to be in the same order unless you figure out a mechanism to disseminate all of the inputs to all of the replicas, and to make sure that they all know the order to play them in. And that shouldn't be surprising, because we already knew that from replication of key value stores, right? If everybody knows the reads and writes, and also knows the order in which the reads and writes happened, and it is a total order, then everything's fine. Right? So that's cool. That means that any computation that can be sort of finessed into being a state machine, and a great many can be replicated. Before we talk about, and obviously that mechanism is going to involve dissemination of the inputs to the replicas and choosing an order, right? Why might we be concerned about this restriction? What sorts of computations do we do with computers that don't have the property that they're deterministic? So far in this class, I think this is true. Yeah, so far in this class, I have tacitly assumed that all computations that happen locally are deterministic. In fact, I even said things like, the state of this program at this time is completely a function of all the messages that it could receive. Right? That's only true if the computation running on this timeline is a deterministic computation. Right? So I've been assuming that computation on timelines is deterministic, and all the non-determinism that we've been studying in this class is happening between the timelines. Right? The non-determinism is like the order in which messages get delivered, and whether messages get delivered, and whether computers crash or not. Those are the sources of non-determinism. But I've always assumed that the things operating on the lines were indeed state machines in this sense. Buy that? Okay. But why isn't that always true? What isn't deterministic that we do all the time?
Check the time.
Yeah. So checking the time is certainly not going to look the same every time we run the program, we hope, in a reasonable world in which time moves forward inexorably. What else? Yeah?
Parallel computation, for example.
That's absolutely true. Probably what I would say to that is, I would prefer that if we're going to model parallel computation, we imagine a bunch of different lines. And then that makes it easier for us to model. But you're right, absolutely. The same non-determinism that could come about touchdown order in the network could happen about touchdown order on the bus if we're doing a shared memory computation, right? The exact same issue. What else? Yeah?
Well, sending and receiving messages is non-deterministic.
Well, no, but I'm saying like, the time at which a message is received is non-deterministic. But that's not part of our program. We're not like using non-determinism in the program. But user input, where do I even begin with that? So like, not only is user input probably not, like it might or might not be deterministic. but it's not predictable in some very important sense. And a lot of the time the user input argument comes down to, at some point when you're studying a system, you draw a box around the system. I talked about this before, and you talk about, there's things outside the system, and there's things that go into the system, and there's things that go outside the system. You have to admit that, yes, there's a process generating inputs that maybe I have no control over. But I would never say, like, and then, so in that sense, this thing is not deterministic. However, subject to a particular input, I might or might not have the expectation that the computation itself is deterministic over the input, right? And so it's very often the case, I'm going to hand away, no, inputs are outside the scope. You give me an input, and then I'm going to ask the question, is the box deterministic or not? There's a really important source of non-determinism that nobody's mentioned yet.
Random.
Yeah, so like, sometimes non-determinism is not an evil to be avoided, right, but a tool that we use in our programs to make our programs better, right? So anti-entropy flips coins about what nodes to connect to. Anti-entropy is not a state machine, right? Because you run it 10 times, it'll do a completely different viral propagation of the information graph across the network, right? So, but maybe more fundamentally, quick check works good because it randomly chooses the pivots. Randomness is a computational tool to make the worst case less worse, right? So that's a pain in the ass. So what do we do about the fact that some of our computations flip coins, and some of our computations roll dice, and some of our computations check the clock? What are we going to do? Can we not ever replicate those computations using state machine replication, or is there some kind of neat trick we could do? Is there some kind of neat trick? Yeah.
Probability.
What do you mean?
Like use probability functions, like say that you have a specific input that happens 60% of the time versus 40% of the time.
Are you suggesting that what you're saying is, given a state and an input with a particular probability, make this into a non-deterministic automaton and associate probabilities with the transitions? I don't know if that would help though, because like if that were true, and I made multiple copies of the state machine and fed them the same inputs in the same order, I would only be able to make a probabilistic argument about the likelihood that they were in the same state, right? I wouldn't be able to make sure that they were in the same state.
We could complete the non-deterministic computation on one machine and send it as inputs to the
So, I mean, it's not so much about what machine you do it on, but the point is if you could somehow rewrite your algorithm in such a way that you check the clock, flip some coins, you know, do the Ouija board, do the I Ching, do all those things, and then treat them all as inputs. And then you ask the question is, if we have reified the non-deterministic things, like the value of the clock and the values of the 100-sided die, as inputs, then we may ask whether the state machine is deterministic or not. And if it is, we can still do this. So we have to push the non-deterministic computations just to the outside of the box that we have said is the. Right? You buy that? It doesn't always work. Because sometimes it's not meaningful to check the clock here. It's only meaningful when you check it right before the operation. Right? So this won't always work, but it will very often work. And this is sort of the canonical trick for making something as deterministic as it possibly can be. Non-determinism is just an input. Everybody with me? Okay, so let's talk for a moment about how, once you have an arbitrary computation that you have coerced into being superficially or pseudo-deterministic in this fashion, clients obtain total order from an ordering oracle. And disseminate to all replicants. So like in quorum replication, the clients do a little more work. Clients know who all the replicants are. And it's the clients that are responsible for making sure all the replicants get all the data. So the way you might draw this is here's O. Now, as we've said before in this class, You wouldn't put O on one machine. You would put O on a bunch of machines running an agreement protocol so that they could tolerate faults and nevertheless agree upon one total order. And that's going to be the subject of the next couple of weeks in this class. Then a client communicating with a collection of replicas that, like in quorum replication, are essentially indistinguishable and symmetrical from each other. There's nothing special about any of the replicas. If a client wants to do a write, and let's just say, just to keep things symmetrical with the other examples, that the state machine we're replicating is a data store that does reads and writes over variables. Because if we can replicate any computation, we can certainly replicate the ones we've been studying so far. So client Clarissa wants to write x equals 1. She says, can I have a number, please? Sure, you can have 1. 1. X equals 1. When she gets acknowledgments from all the replicas, she knows that it's been durably stored and that we can tolerate the loss of 2 of them. If she wants to do a read, she can direct it to any replica. It doesn't matter which one, and get a response back. Note that the reads don't need to, note that the reads can go to any replica, and it doesn't matter, because they're only going to be reading whatever writes came before it in the total order. We can also do the same tricks we did with primary backup, where I can fire off requests before I hear the responses. Oh, this is going to be 2, and I can fire off 2 before I know about the status of 1. And I get the guarantee that 2 will be applied after 1 on all other replicas, even if it happens to arrive earlier. Why? Well, because we got 2 before we applied 1, right? So then we get 1, we apply it, and then we apply 2. Right? So how is this picture different? Well, in some sense, I've taken part of the role of the primary in primary backup, the job of deciding the total order, and I've given it to O. And I've taken another part of the job of the primary, disseminating all the updates to all the replicas, and I've given it to the client. So what used to be the primary is now split over the ordering oracle and the client. And all the replicas are just acting like backups in primary backup, right? All they do is acknowledge. Make sense? That's pretty much all there is to say about state machine replication. It's very powerful. It's very powerful because you can replicate an arbitrary computation. This is kind of like the holy grail for really nice, complicated computations that were designed to run on one computer. And we're in a position in which we have some budget, and we'd like to make them more reliable. We can make them more reliable in a very straightforward way by throwing hardware at them using state machine replication. Now, needless to say, just like in primary backup replication, O is going to be a bottleneck that bounds the throughput of this system. We're only going to be able to do as many writes or reads per unit time as O can dole out those sequence numbers. This is very often going to be the case, and there's been some really interesting work in recent years in which O is actually implemented as a cluster of specialized hardware at the network level. Like you've implemented O like in the level 2 switches, for example, so that as packets traverse the switch, they automatically get sequenced at hardware speeds to try to alleviate that bottleneck. Because otherwise we have a lot of potential parallel resources. We could have a lot of clients doing a lot of I/O, but they're all going to have to go through this fundamental model. Questions about state machine replication? Yeah.
Yeah, so you said the Oracle was the one here that established the orders of the writes from the client.
Yeah, actually, thank you for asking. I lied. The Oracle is going to be required, I was just thinking about that as you said it. The Oracle is going to be required to decide the order of the reads as well. Right? So the client gets the order of its read, but it only needs to send the read to one replica. But it has to know the order with respect to the write. Yeah?
So you said in terms of implementation, you typically would build the Oracle into like the network infrastructure?
Oh, I'm not saying you typically would. I'm saying there's been emerging research, cutting edge things like that professors write about, not that people are doing at Google right now, I think. But yeah, there has been interest in hardware speed sequencing because we know that the switch technology we have can put numbers on packets at almost 9 speed. Yeah. Yeah.
So is recovery also tricky? Because once you lose O, you lose all the order.
Oh, right, but the technique would be to make it so that you do not lose
Right. So you focus on like maximizing the time.
To be fair, in the event, let's talk about that for a minute. Let's say that you did lose O. Oh, wait a minute. So nobody has any idea where O's sequence was at. But then somebody comes along and creates a new O. What would you do? Like, what would a protocol look like to reconcile?
See what C says.
What? Start over at 1? Well, that might or might not work, because like clients received acknowledgments that their writes were durably stored, and now they've left the building.
Ask the replicas what the last write was.
Yeah, okay, so you ask the replicas what the last write was, and they give you back numbers. And what do you do?
The highest
The
one.
last one that's strongly consistent is the one you roll back to.
Yeah, I think that's, I haven't thought about this, so I'm kind of going, wait, so like, you're right, so like, one approach would be to say, the next one should be the highest one you saw plus 1, but that only works if that last one actually made it to everybody. And this resembles primary backup recovery, right? You kind of want to say, well, how could things have happened? You could have finished something and then died before starting another thing. Or you could have died in the middle of doing something. It seems like those are the only two possibilities, right? And if the first thing happened, that's fine. If the second thing happened, as we discussed a bunch of times in this class, you have two choices. You finish it, or you roll it back. And typically rolling back is a little safer, easier. So probably, but you would have those two choices, right? Because you'd be like, okay, well this guy's seen up to 7, but these two have only seen 6. Well, you could, if this guy has 7, well the thing is he could have gotten 6, he could have like written a partial record to his, who knows? You could give these guys the updated values, and then your new sequence number is 8. Or you could be like, nah, that didn't happen. The current sequence, and that seems easier, right? Because now this guy's just going to give 7 to somebody else, everybody's going to get 7, nobody needs to roll anything back, except this guy just clobbers what he had there before. But I think it's a big design space, the point is, right? There's no right answer. Yeah, sorry.
How about like reading the inputs from each replica and try to get the oracle back to the previous state? Does that not work? Or
well, that's what we just discussed. It's just that let's say the new oracle goes out to everybody and says, "What's your sequence number?" And these two guys say 6, and this guy says 7. What should we do? So that was the conversation we were having, right? So I don't know. I mean, what I would do probably, but it's a big design space, is I would just say, okay, the next number is 7. And then that means this guy's going to have to change his mind. That means that last write that made it to only one of the replicas, it's like it never happened. The other alternative would be to try to update R1 and R2 with whatever the value associated with 7 was. It's a little bit more complicated. It might be worse. Good? Yeah.
What happens if packet 7 was like en route to the rest of the replicas and they send back saying 6 is my highest, and then they get 7, and then like does the oracle have to say if you get 7, clobber it? Or
Well, so yeah, I think it's a good question because it's the sort of question we should be asking, right? Which is that this person sent back 6, but the thing is, there was a message from way out here that was just taking super long, and then like it eventually gets there, right? So immediately after saying the highest thing I saw was 6, now the highest thing I saw was 7. But this would be fine if we did the recovery I just described, because now 2 replicas need to throw away 7 and replace it with the new 7 rather than just
so
1.
just everyone gets told roll back 7.
Yeah, or maybe you don't even need to roll back. You just say, look, whenever you get a thing for a particular number, you put the thing in that slot, whether or not there's something there already. Right? And that would, in this case, that would just work. And it would work, in fact, if the same thing happened. They all had 7, but at the time the oracle asked them, they didn't all have 7. Now none of them have 7, and that's fine. Is that fine? It is fine, because the only reason it wouldn't be fine is if the client had gotten an acknowledgement that everybody had 7. Because then the client's write durability, it wouldn't have been durable. But that wouldn't happen because the client wouldn't get the acknowledgement that everyone had 7 until everyone had said that they had 7.
Well, it seems like you would be able to get into a space where the client gets its packet ID, sends its write requests, the oracle dies, and then the client gets acknowledgements that are in flight. Like the client writes are in flight, and then the oracle is restored. And the client has then written 7s.
Hold on. So I'm pretty sure that what I said is true. I think we won't get to agreement today. That's okay. This is good stuff. But so we have this oracle, we have a client, and you're saying, let's just have 2 replicas to make my life easier.
Yeah.
It's 2 replicas, right? And we said, so the client goes, okay, what do you think? Okay, it's 1. And you're saying, so like now, like the oracle dies.
Right.
What you're saying, right? So the client goes out. Now there's two possibilities. The responses, oh, I see what you're saying.
Yeah.
Okay, so here's what you're saying. So the responses come back, and at this point the client's like, okay, that's good. It's acknowledged. And a new oracle comes into being. And somehow,
in order to stay consistent, the oracle needs to have, if these messages are written to the replicas, then the oracle needs to have their record. And
but it will, like, so you're saying that the oracle came out.
So the oracle.
The oracle woke up. He got almost no. Wait, he died here.
Right.
And woke up here, and he like came out and hit like here.
Yeah, exactly. He gets. I've never seen a message as what the replica said, but the client message, the writes were in flight.
But then, meanwhile, this one gets there in time. Right.
Well,
maybe
in some
this
sense,
whole recovery protocol doesn't work at all.
Yeah.
So we invented it just now on the fly,
Yeah.
right? So we shouldn't be surprised
Yeah.
if there's holes in the protocol. You know, as I'm doing this, I'm like, oh fuck, this really looks like Paxos kind of. You might need Paxos for this. Like, this is starting to look a lot like Clay. I'm going to teach in a couple of days. Yeah.
And what is the reason why we don't commit at the oracle? Is that just because otherwise you just make primary backup?
What do you mean commit at the oracle?
When the replicas.
Well, because in some sense, like when the oracle is given out a sequence number, that doesn't say anything about the data having been written to anybody's disk. It doesn't say anything about the data being durable. When we talk about a commit point in primary backup or chain replication, at the commit point, the node at which the commit point happens knows that henceforth the data is stored on enough replicas to tolerate failure.
Okay.
Right? When a sequence number says, sure, you can use number 1, they don't know anything about the durability of your data. So we wouldn't call this a commit point. The commit point is here.
Right.
Like,
So yeah, that's what I'm saying. Is the reason why we don't commit, like the commit, I guess, the replicas responding, enough replicas responding to the client, is the reason why we don't do it to the oracle? Is it because like the response?
Because the client is the one who needs to know that the data is durable. Remember that the client, even in primary backup, the client went to the primary went to the backup, but ultimately the primary went back to the client. He said the commit point was here on the primary, but obviously it was the acknowledgement to the client that said the data is durably stored. Okay. Right? So the oracle, all the oracle's job is to maintain an integer and to update the integer every time somebody sends her a message. Right? So that's all she needs to know. She doesn't need to know the commit status of those things.
Okay.
To be
Yeah.
Could the oracle ask the client of the most recently committed message?
In this picture, sure, but in practice there could be millions of clients, right? So not necessarily, right? So I don't know. Let's stop because like I want to move on, and you know we could invent another protocol that didn't work. But this is all good. You know, like in some sense, this is a pattern, right? You go, oh, okay, if something's gone wrong, maybe we can kind of stop doing operations and do like a sort of reconnaissance phase in which we go look at what's out there, and based on what comes back, we do things. And this is a great segue because now we're going to start talking about two-phase protocols for the first time. Protocols in which you go out and see what's going on, and based on what comes back, you go out again. Paxos and two-phase commit and all this good stuff is all going to have this flavor. And this flavor of protocol is fraught with peril due to these kinds of race conditions, due to messaging. Okay. Agreement. Agreement is super hard. Two really important ones that we've that these are like terms we've used in this class a bunch of times without really defining them. And I'm going to argue that these two things are actually kind of duals of each other, actually.
Mm-hmm.
You can buy that. Mathematical duals of each other, right? Because the leader election problem is, given a collection of communicating machines in a distributed system, choose one of them, which hasn't failed, to be distinguished, to have some distinguished role. Don't choose 2, don't choose 0, choose just 1. It's going to turn out the best ways to do this is to get all the computers to talk to each other and work together to choose 1. And obviously, you want to choose a computer that is up, right? The dual problem, of course, is failure detection, which is like, I want not one computer that is up, but all of the computers that are not up, right? If you had a good leader elector, you might be able to use it to implement a failure detector, and vice versa. If you had a failure detector, you might be able to use it to build a leader elector. It turns out, I'll put this down here, if you had an implementation of a sort of meta algorithm, we're going to study a lot in this class, called consensus, you could use that as an oracle to implement leader election or failure detection. I also mentioned a little bit on Friday this problem of atomic commitment. Right? The idea being you want to do some kind of compound action on more than one machine, but you want it to be the case that that action appears to either completely succeed or not happen at all, despite the fact that some of those machines can fail. And so you shouldn't be surprised to hear, if I have two machines that can fail independently of each other, one can fail and not the other, or the other and not the one, and I want to do some atomic thing involving both these machines, like, oh, I don't know, move a piece of data from one to the other, atomically, it shouldn't surprise you to hear that they can crash along the way. This is hard, right? Does it surprise you to hear that? Why did I say that? Why is it hard if Alice can crash and Bob can crash to move a data item from Alice to Bob atomically?
Because they can crash.
Okay, so why is that? What are you so afraid of?
You tell Alice to move the data, Alice moves the data, like sends the command and then crashes immediately and Bob never gets it.
Well, that's fine because all I said was it has to be atomic. I didn't say it has to happen. So if I say something has to be atomic, you always have a safe way out, which is you just don't do it. You can always do that. So in your case, you were fine because it didn't happen. It was like the tree never.
Are we including like an acknowledgement as well? Because is that?
Well, I haven't said anything about the protocol, so you could invent a protocol. But my question is like, what are you afraid might happen? Yeah.
Well, we might have like a multi-megabyte item that B writes to disk, and halfway through writing to disk, B crashes, and so you have a corrupt data.
Yeah, so that's good. So I think like what you've done is you've made what I was assuming would be an atomic operation, writing something to the disk, and you said that could be compound too. But I'm going to say to you, even if writing a data item to the disk was an atomic operation that either succeeded or failed, we've got a problem. And it doesn't have to do with disks and big files. It has to do with the fact that Alice and Bob are different computers and we have partial failure. Yeah.
Alice sends the data and deletes it, and Bob crashes before getting it.
Yeah, that's great. So like, how do you implement move? Well, the only primitives that you have are addition and deletion of things, right? So the way you would implement move is you would say, I'm going to delete it from Alice, and at roughly the same time, as close to simultaneously as possible, I'm going to go ahead and add it to Bob as fast as can be, so that somebody who looked at Alice after her deletion, but before my insertion, wouldn't perceive that it was in no place. And similarly, somebody who looked here real quick, you know what I mean? So like, let's just imagine that you could do those operations close to simultaneously enough that the visibility wasn't a concern. And what is the concern? Yeah.
Is there a problem if the data happens to be both on Alice and Bob at the end of this?
Sure. I mean, that would mean that it wasn't atomic. That would be the other problem besides the data being in neither place. That was kind of what I said. If this happened first and then that, it could be in both places. But let's imagine that we can make these operations happen close to simultaneously. I'm not saying you could. I'm just saying let's imagine you could. We can make them happen close to simultaneously enough that you would never be able to perceive that. There's still a problem, which is that I could crash Alice, right? I could crash one of these computers. You know, I could like successfully do the deletion from Alice, and I could fail Bob, right? And then I would have no way to undo the deletion, right? So now the thing's gone. I've lost it, right? So doing things atomically is hard in the presence of failure, precisely because a compound operation involves two computers, and I can't make both the computers necessarily be up for the duration of the compound event. Okay? spend the rest of the day today talking about the commit problem, and we'll get back to leader election failure detection and consensus later. No, actually, that's a lie. I'm going to frame agreement a little bit more generally, and then I'm going to dive down into commit. Any agreement protocol is going to sort of graphically implement a gadget that looks like the following. There are a multiplicity of potential inputs for the gadget. These could be, presidential candidates, or machines who are candidates to be the leader. Actually, it's very similar to a presidential election. Or these could be readings from the sensors on my airplane or something like this. It's like a roach motel. Many go in, one comes out. No, that's not a roach motel. Roach motel, none come out. Right? So anyway, many go in and one comes out. And then you can imagine this is sort of the single site version, but the distributed version of this would be like a bunch of computers, Alice, Bob, and Carol, all running consensus. And they all come into the game with their own opinions about what they would like the consensus to be. And they all come out with an opinion about what the consensus is, with the constraint that these had all better goddamn well be the same opinion. Okay? And to write this down in English, any agreement protocol attempts to provide three key properties. The first one, unsurprisingly, is called agreement. The agreement property says, if any of these boxes output a variable, let's just imagine that the only inputs are ones and zeros, keep our lives simple. If any of these guys output a 1, everybody else better output a 1. That's what agreement says. No disagreement. Easy enough to achieve in general, right? I can just always output 1. Validity, which is sometimes called, you may find if you go on the internet, which I say you shouldn't do, non-triviality. Which says that the output must have been one of the inputs. So for example, if Alice thought it was a 1, and Bob thought it was a 0, and Carol thought it was a 0, and they all decide 1, that satisfies agreement, and it satisfies validity, because 1 was one of the inputs. I never said anything about majority or anything. It just had to be one of the inputs. Now, why? What's this validity crap about? Why do we need to have a rule like validity to define an agreement protocol? I'm going to argue that without it, it's nothing. Yeah?
Because if A says 1 and B and C says 0, and the output is always 4, then you have an agreement. But nobody actually said
Good.
that.
It would be easy, but trivial, to implement agreement without validity.
Right.
For the reason that you just said. Because I have created a new consensus algorithm. It immediately reports that the decision is foo, irrespective of the inputs. Oh, let me also add, the last thing is termination. We would like it to eventually decide something, please. Okay? So if I do foo, it terminates. In fact, it terminates fast as hell. It's the world's fastest consensus algorithm. And everybody agrees. But it trivializes.